So yeah, so when we talk about electron affinity, so first of all, we have to understand the basic definition. What is the meaning of electron affinity? Now, as we can see that when we talk about electron, right? Sorry, when we talk about an atom, so we know that if this electron of outermost orbit, right, needs to be sent outside, means outside the atom, then some energy must be supplied, and that energy is your ionization energy. But if one electron is added to the atom, is added to the outermost orbit of an isolated gaseous atom, then energy will be released, right? Okay. So usually energy is released when one electron is added to the neutral atom. Okay. In some cases, it may be absorbed also. That's why we will say energy change. Okay. So I can say that the energy change when electron is added to the outermost orbit of an isolated gaseous atom, okay, is called your electron affinity or electron gain enthalpy. Electron gain enthalpy. Okay, so I can say that the energy released on adding the electron, right? 1 mole of electron or 1 electron. Okay, so it depends on the unit, right? If it's energy per mole, then you have to say 1 mole of electron. Okay, or you can just say 1 electron also, it's fine. Okay, to neutral atom of the gaseous form. Okay, that's why the definition should be outermost orbit of an isolated gaseous atom. Then that energy is called as electron gain enthalpy or electron affinity. Okay, right? So see example. Here we have A, which is gases, right? This is a neutral atom. Then after receiving 1 electron, it will form A minus. It will form an anion. Okay, right? So the energy change, this delta H, is your minus En. Okay, En is just any number, right? Any value it would be. This is called your electron gain enthalpy, delta Eg, which is your electron gain enthalpy. Okay, right? So what is electron gain enthalpy? It is the energy change, right? It is the energy change. When 1 mole of electron or 1 electron is added to either 1 mole of neutral atom or 1 neutral atom in its isolated gaseous state. Okay, any issue in that? So all of you understood what is the basic definition of electron affinity or electron gain enthalpy? Just raise your hand. If you understood the basic definition, just raise your hand. Okay. So all of you understood, right? If anyone have any doubt, please message. Okay. Now, as I said, instead of writing energy released, you should, okay, I'll explain again. Okay, so it is the energy change. Instead of energy released, it's better to say energy change. Why? Because in some cases, energy is absorbed. For example, in case of inert gases, okay, because inert gas is already fulfilled, it is not easy to add electron in inert gases. Okay, So in that case, you have to supply energy. Okay, in that case, you have to supply energy. So I can say that electron gain enthalpy is the energy change. Remember this. It is the energy change when one electron, right, or 1 mole of electron is added to one atom or 1 mole of atom in its gaseous state to form a stable ion, right, or anion. Make sense? So it is the amount of energy change when 1 electron is added to isolated gaseous atom. Okay, Amish, Nishita, Samya, you understood this? You understood now what is the basic definition of electron affinity? Okay. Now, as I said, that it may be positive or negative. Okay, that's why you should not say it will be negative always. Now, when we talk about electron affinity, if 1 electron is added to the neutral atom, then it is called as first electron affinity, right? For example, if I'm having A plus electron, so we will get A minus, right? So in this case, delta H will be your first electron affinity, right? But when this A minus accept another electron, it will form A2 minus, right? So this would be your second electron gain enthalpy or second electron affinity. So delta HEG, right? Where delta HEG is your electron gain enthalpy. So for first electron gain, it is delta Eg1, and for second electron gain, it is delta Eg2, delta HEG2. So I'm saying that delta HEG1 means first electron gain enthalpy, right, will be mostly negative. Okay, except for some exceptions, but mostly it will be negative, right? But delta HEG2, okay, it may or may not be negative. It may be positive, okay, it may be greater than 0 or maybe less than 0. Okay, now why this happens? See, when you added 1 electron, okay, when you added 1 electron, the electron density in the atom increases, okay, and now the second electron which you are adding face extra repulsion, okay. Now because of that, because of the repulsion, right, sometimes you need to supply energy, okay. That's why second electron gain enthalpy is positive. So I can say that, see, if 1 electron is added, if 1 electron is added, okay, it get converted into negative ion, okay. But when you add 1 more electron, there will be repulsion between the negative charge atom and the electron, okay. And in order to overcome that, energy should be supplied. Got it? Everyone understood this concept? Just raise your hand. No one is having doubt, right? Okay. So I said that when we add 1 electron to your neutral atom, okay, when we add 1 electron to your neutral atom, it converts into negative ion, okay, it converts into negative ion. Now After that, if you add one extra electron to the negatively charged ion, okay, the negative charge ion will repel the electron. There will be repulsive force because negative charge will repel negative charge. Na? Okay, so this is the example I'm saying, Karishma. Okay, so you can just take example of oxygen. So I can say that, I don't remember the value actually, so I'll just giving you the example. So the oxygen after adding one electron will become O minus. Okay, so in this case delta H would be negative. But when O minus will gain one more electron to form O2 minus, now in this case delta H may be negative or positive. Okay, so why this happens? Now this O minus is negative charge ion and this electron is also negative charge. So if it is approaching this O minus, there will be repulsion. Okay, and in order to overcome that repulsion, the energy is added. Okay, that's what I did, Sneha. Okay, Sneha, you understood this? See, I'm saying that if I'm having a neutral atom, suppose neutral atom is oxygen here. Okay, if I'm adding one electron, it is converting to an ion O minus and delta H in this case, delta H is negative. Okay, means energy is released. But when you talk about O minus, okay, if we add electron in O minus, because of this repulsion, there will be difficulty in addition of electron. And in order to overcome this repulsion, the energy should be supplied. So in this case, delta H will become greater than 0. Okay, so I can say that first electron affinity or first electron gain enthalpy is negative, but second electron gain enthalpy is positive. Okay, right? Now understood this? Everyone? Pritam, Jitendra, Mansi, Anjali? Yes, I'm just giving example of oxygen now, right? So obviously, in case of oxygen, it is negative. If it will be any other element, it may be positive, may be negative. Okay, right? So I guess everyone got this. Okay. Now, this is the basic definition of electron gain enthalpy or electron affinity. Okay. Now, on what factors it depends? So, this also depends on your effective nuclear charge. Okay. So, obviously, if the atom has more tendency to more tendency to attract electron, okay, right? It will try to accept electron, hence the energy released would be more. Okay, so I can also say that electron affinity is directly proportional to effective nuclear charge. Okay, so I can say that electron affinity is directly proportional to effective nuclear charge. Okay, so both ionization energy as well as electron affinity is directly proportional to effective nuclear charge. That you should remember. Now, we know that size is inversely proportional to effective nuclear charge. So obviously, electron affinity should be inversely proportional to atomic size. Okay, right? Because when you talk about the size, if size becomes bigger, the attraction of the nucleus decreases, Z effective decreases, and the electron, right? When we add electron, there will be less release of energy. Okay, so I can say that electron affinity is inversely proportional to atomic size. Okay, so yeah, this you have to remember. Now, what do you think about the shielding effect? Okay, same as ionization energy, same ionization energy. Everything is related with Z effective. When screening effect increases, Z effective decreases. Okay, and as Z effective decreases, the electron affinity will decrease. Okay, so that's why I told you to remember the basic concept of Z effective, effective nuclear charge, because all the properties are based on effective nuclear charge. Okay, so screening effect or shielding effect increases, Z effective decreases, hence electron affinity decreases. So I can say that electron affinity is also inversely proportional to shielding effect. Okay, sorry, something happened. Wait for some time, it might be my internet. So all of you understood this concept till now? Okay, okay then. Just take 2-3 minutes to understand this concept. If you want to write it down, you can just write it down. Okay. Yeah. Okay. So this is the general trend. This is the general order. Okay. This is the general order. So you just have to focus on effective nuclear charge. Okay. That electron affinity is directly proportional to effective nuclear charge. So whatever the factor will affect the effective nuclear charge, it will affect electron affinity accordingly. When atomic size increases, effective nuclear charge decreases, hence electron affinity decreases. If shielding effect increases, effective nuclear charge decreases, hence electron affinity decreases. Right? Got this? Everyone got this? Karishma, you understood now? Okay. Now, when we talk about individual elements, this is your general trend. Now, we know that according to these concepts, generally left to right, when you go from left to right, okay, when you go from left to right in a period, size decreases, hence electron affinity increases. Electron affinity increases, right? When we go from left to right, size decreases, electron affinity increases in a period. In a group, when you go from top to bottom, size increases, hence electron affinity decreases. This is your general trend. Okay, this is your general trend. But when we talk about elements of second period, just see the elements of second period. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay. So according to general trend, the order should have been this: neon greater than fluorine, greater than oxygen, greater than nitrogen, greater than carbon, greater than boron, greater than beryllium, greater than lithium. But obviously it is not right, it is wrong, right? Okay, why it is wrong? So we'll see the electronic configuration of each element. Okay, now when we talk about lithium, so lithium is 2s1. I'm just talking about the outermost orbit. So 2s1, one electron in outermost orbit. Beryllium 2s2, boron 2p1, then carbon 2p2, nitrogen 2p3, oxygen 2p4, fluorine 2p5, and neon 2p6. Okay. Okay then. Now we will see each element, okay, according to its configuration. We'll start with neon. Now when we talk about neon, it's all the atomic orbital is already fulfilled, okay. It's 2p6. So I can say that in case of neon, all the p atomic orbital is fulfilled, right? So obviously there's no space where one electron will be added, right? So obviously if there's no space, the electron affinity should be minimum. Okay. So I can say that in case of neon, neon will have least electron affinity. Neon will have least electron affinity. So neon less than. Now after neon, fluorine, C fluorine 2p5. If we add one electron, it will become fulfilled. And according to general order, also it is maximum. So fluorine is maximum. Fluorine greater than. Again oxygen, right? Now after oxygen, we have nitrogen. Okay. Yes, that's the thing, right? So nitrogen is already half filled. Okay. So now it is half filled. Electron can be added because only 3 electron is filled in the p atomic orbital. So 3 more electron can be added, but the stability will decrease. Okay. Now because of that, it will not have higher electron affinity. It will have lower electron affinity. Okay, so N should not be after oxygen. Okay, now see about carbon 2p2. Okay, now after gaining one electron, it will have half filled configuration, so it will be stable. So obviously it will try to take electron. Okay, so after oxygen we will have carbon. After electron we will have carbon. Good then. Now after carbon we have boron, which is normal. Okay, beryllium is already fulfilled, but think about lithium. Lithium is half filled, but after gaining one electron, it will become fulfilled, right? Which will increase its stability, right? So after carbon, we will have lithium. Okay, after carbon, we will have lithium. After lithium, we are left with beryllium, boron, and nitrogen. But beryllium is fulfilled and nitrogen is half filled, and boron is normal. So boron, then nitrogen, right? And at last we will have beryllium and then neon. Okay, see, if you're not getting it, you just have to remember the order. Okay, you have to remember the order. Okay, why this order? Because of their electronic configuration. Okay, half filled and full filled atomic orbitals are more stable, so they will have less tendency to accept electron. Now because of that, the electron affinity of half filled and full filled atomic orbitals will be less. This is the concept. Okay, right? So why this order is there? Because of half filled and full filled atomic configuration, electronic configuration. Okay, got it, Karishma? Okay, now the order is this focal, but the order is focal Banabeni. L focal, BN Bana, BENI, Beni. Got it? Just think about this. Just take 2 minutes and think about this. So all of you getting this? Just raise your hand. If you got this, just raise your hand. You have to remember this order. I've explained how this order is obtained. Okay. Okay. If anyone have any doubt, right, just ask me. Okay. Why this order? Because higher stability of half filled and full filled atomic orbital. Okay. And due to that, there will be less tendency to accept electron, and electron affinity would be less. Got it? Okay then. So this is your normal trend and actual order. Now, this is applicable only for S and P atomic orbital. Okay, S and P block. Okay, so this is the order for second orbit, second period, right? So all of you can have the same order for third period. Okay, for example, instead of fluorine, we'll have chlorine in third period. So chlorine greater than oxygen, sulfur, carbon, silicon, lithium, then sodium, boron, aluminium, nitrogen, phosphorus, beryllium, magnesium, neon, argon. Okay, so see this. Argon is AR. Wait. Okay, so you understood the order, right? Anyone have any issue in that? Just raise your hand. Okay then. So when you talk about periodic properties, you should remember general trend, then start adding exceptions. Okay. Now this is the general trend across the period of S and P block elements. Okay. Now we will see exceptions one by one. So I guess all of you got this. Yes, yes. Okay. Now see, first exception. As I said, this half filled will have less electron affinity. Okay. Okay. So this is the first exception. On in going from carbon to nitrogen, okay, electron affinity decreases instead of increasing because of half filled atomic orbital of nitrogen. Okay, this I have already explained. And third period, same thing will happen. Okay. Same thing will happen in third period. Okay. So the first point, second point, third point is already covered in the order of second period elements. Okay, fulfilled, half filled will have less electron affinity because of higher stability. Okay, and electron affinity of inert gas is 0. Why? Because it is already fulfilled. Okay, right? So all of you understood these 3 points? Wait, what happened? Okay, okay. So the first 3 exceptions is already cleared. Okay, first 3 exceptions is already cleared in this order. Okay, now fourth exception. Just star mark this fourth exception. No, fourth exception is also cleared, sorry. Fourth is also cleared. Fourth, the same thing. Beryllium and lithium. Okay, see, the electron affinity goes on decreasing from 1A to 2A. So basically 1 is your first group and 2A is your second group. Okay. Now see the example here.